Everyone. We had a short break. I think it is time to start now. I'm Uzay Kaymak from Eindhoven University of Technology. I will be chairing this session. And it is my great pleasure to introduce today one of the pioneers of fuzzy modeling, Dr. Jishin Roger Jang. Dr. Jang received his PhD from Electrical Engineering and Computer Science Department at UC Berkeley, where he worked together with FUZZ-IEEE on fuzzy logic and neural networks. Now we have seen actually during the panel at the end when there was this questions, what are the largest or most important developments, and two things came up there very prominently: Takagi-Sugeno modeling and FUZZ. And I think you all know Dr. Jang from his work introducing the FUZZ, so the Adaptive Neurofuzzy Information Systems. And in doing so, he gave a big boost to the development of the neurofuzzy systems field. Now, to this day, as far as I can judge, FUZZ remains one of the most popular methods for learning Takagi-Sugeno systems from data. And I know that my students actually are very fond of it, so they keep on using it. After his PhD, Dr. Jang joined MathWorks and co-authored the Fuzzy Logic Toolbox for MATLAB. I think fuzzy systems researchers all over the world have used at one time or another this toolbox that he was really instrumental in developing, and it was also a crucial contribution to the tool set of our field. Now, since then, Dr. Jang has developed a keen interest in implementing industrial software for machine learning, and he maintains various toolboxes, amongst others for machine learning and speech and audio processing. He is the co-author of more than 300 papers and has organized multiple symposia and conferences. He is also the co-author of the book entitled Neurofuzzy and Soft Computing, published by Prentice Hall. Now, Dr. Jang's original 1993 paper on FUZZ has received over 22,000 citations. This paper and his contributions to the Fuzzy Logic Toolbox for MATLAB earned him the 2025 IEEE CIS Fuzzy Systems Pioneer Award. Now, his research focuses on both the theory and the practice of machine learning, with applications spanning fintech, so financial technologies, speech recognition, natural language processing, healthcare data analytics, computer vision, and music analysis, so very broad. Previously, Dr. Jang has been a professor at the Computer Science Department of the National Tsinghua University in Taiwan, and since 2012 he is a professor in the Computer Science and Information Engineering Department of the National University of Taiwan, the NTU. He directed NTU's FinTech Research Center from 2018 to 2022 and served as the IT director at NTU Hospital from 2017 to 2019. Currently, Professor Jang is the Chief Technology Officer of the eSun Financial Holding in Taipei, where he leads the AI-driven banking innovation. Now, clearly, we have a true pioneer amongst ourselves, so please join me in giving him a warm welcome.
It's really nice to be here, especially after so many years without doing fuzzy research, and I'll tell you why. So today I'm going to talk about learning paradigms in fuzzy systems. So first, I'll spend a few slides in memory of Professor Lafizade, and I'll briefly go over the learning paradigms in fuzzy RAN. And also I'll give you a quick review of FUZZ in perspective, especially the learning algorithm, feature selection, and outline detection. And I'm going to focus about the explainability of FUZZ. Then I'll show you how come the fuzzy set is indispensable. During the panel, I think some of you are worried about the future of fuzzy logic. I see no reason, to be worried about it, because it's always there, whether it's called fuzzy logic or not. So, as you can see, here we have some photo of Professor Zade. When I first approached Professor Zade for my PhD advisor, he told me that, Roger, I'm very busy. You have to do independent research. At that time, he is already 70 years old. And actually, I don't know what does that mean by independent research. Eventually, I know that he has to give more than 50 talks every year. And the talks is all over the world. So he is flying all the time. I didn't get much chance to see him. And but sometimes he does need to come to see me because he want me to prepare his transparency. I'll show you some of the transparency. And at that time we have so many visitors. Some of them from Taiwan, from mainland China, from Japan, from Singapore, and from Spain, from Russia. So actually he is a people person. He always like to be people around him. So this is some of the manuscript, I got from Professor Zade. And this one is like a dispositional fuzzy theorem. The next one is a categorical fuzzy theorem. It's hard to recognize. You always use a pencil and use a rubber to erase it. And this is from crisp to fuzzy paradigm shifts. And this is fuzzified ball and a beam problem. So at that time, by doing his transparency, I got to know his latest thought about fuzzy logic. But his thought is more of the symbolic side. But my research was more like numerical, computation side. So it's kind of different. And November 30, 1991, we have a Google Doodle of Professor FUZZ-IEEE in memory of the day he submitted his fuzzy set paper. Eventually, later on, the paper was published in 1965. That's why we have this 60 years anniversary of fuzzy sets. And of course, eventually he is arrested in Baku. And from the internet, I see there is a monument. So I think someday I'll pay my regards to Professor Zade and to go there. So Professor Zade is really a nice person. Many years after I get back to Taiwan to be a professor, and he come over to give a speech, he never talked about my research or about my work. He always asked, Roger, are you happy with your life? So he is very nice. So one thing I learned from him is to be nice to everyone, even to those who don't agree with you. So I think we should give a big applause to Professor FUZZ-IEEE. Hopefully, he can hear us from heaven. Okay. So here we have some classical learning paradigm using fuzzy logic. I think the first one is fuzzy sequence clustering by Professor Jim Bestek. All the mathematical elegance is in this kind of clustering. That's why eventually I put an animation on the fuzzy logic toolbox. And we have also the reinforcement learning. We have fuzzy reinforcement learning. And yesterday I heard some term about fuzzy deep reinforcement learning. I think in the near future we are going to fuzzy quantum deep reinforcement learning, but I don't know what that means. So everything was pulled together, and eventually we can come up with something new. And for K-nearest neighbor, we have Professor Jim Keller. He proposed the use of the fuzzy version of K-nearest neighbor. And also for linear discriminant analysis, we can have a fuzzy linear discriminant analysis. But I remember seeing this paper somewhere, but too bad I couldn't find the reference in time. So these are all those paradigms. You transform a original classification or clustering problem, and by introducing fuzzy sets, it becomes a fuzzy one. And of course, the computation load is getting larger, but the performance is getting better. So now this is the Takagi Sugeno fuzzy model. We have the one input example. This should be pretty straightforward. We have a 3 membership function. If speed is low, then the resistance is a constant. If speed is medium, then the resistance is 4 times speed, so on and so forth. So I think everyone should be pretty familiar with this kind of Takagi Sugeno fuzzy model. Then again, this is a 2 input example. We have a membership function on X. We have 2 membership functions, A1 and A2, and the 2 membership function on Y. So we got 2 rules. If X is A1, Y is B1, then Z is a linear combination of the input variable. Similar for rule 2. So by using this kind of Takagi Sugeno fuzzy model, you can do fuzzy reasoning. You can find the firing strength of each rule and eventually do a weighted average of the rule's output to derive the final output. So back in 1990, everyone is thinking of how to combine fuzzy logic with a neural network. It's pretty straightforward because in fuzzy logic we can, capture human expertise. But on the other side, for neural network, we can do learning from the data. So if we can capture human expertise together with learning from data, we can create something useful. So at that time, I proposed the architecture of FUZZ. It's called Adaptive Neural Fuzzy Inference System. The fuzzy reasoning mechanism is right here. So we can change all the operation into an FUZZ structure. When I say FUZZ, that means it's a specific adaptive network for fuzzy inference system. I first published the paper in 1991, AAA. I think this is the first paper on neural fuzzy modeling in AAA. I still remember when I finished my presentation, everyone doesn't know how to ask any question because they don't know nothing about neural fuzzy. And then I do some extension and add more simulation example. Then I published in 1993. Hold on, let me change this to be right here. No, it's much better. So I published in 1993 the FUZZ paper. At that time, I have no idea it's gonna become so popular. So, but anyway, as you can see, we have the premise part. The membership function is encoded here. We can compute the product, and we can do some normalization. And then this is the output of each rule, and we can divide it, the weighted sum, by the summation of the total weight to get the final output. At that time, I was trying to generalize the common neural network. So I try to use, the node, each node should be very genetic. So it can use to represent any kind of function. And any parameter can be embedded in the nodes. Even you can share parameter. So by using this kind of adaptive network, it's very easy to represent the the operation and the structure of the whole network. And when I derived the back propagation, I was so excited. I thought I find something new. But eventually, it come to me that there are someone already published the method of back propagation, but it was termed ordered derivative back to 1960 something. And here we have a 4-rule FUZZ. You can divide it the input space. We have a 2 membership function on X and a 2 membership function on Y. Totally, we have 4 rules. This is a very easy partition of the input space. But of course, you're gonna see it's gonna lead to some critical problem. Especially, it will lead to the so-called curse of dimensionality. For instance, if you have a two membership function for each variable, and suppose you have a 10 variable, and it will be 2 to the 10th, will be 1024 rules. It's not bearable. It's computation-wise, it's not feasible in a sense. And if you have read the MP's paper, you can see the original structure is like this. You know, I compute the weight, I pass the weight into a normalization layer to get a normalized weight, and I multiply the normalized weight with the output of each rule and do a summation. This is the implementation of my 1991 paper. But when I went to the method, I think it should be changed to another representation. So I put the summation over there and divided the weighted sum by the summation of the weights. The reason I want to do this is if the membership, if the partition of the input space can satisfy the fuzzy partition requirement, then I think I can simply cut this output, because the summation of the weights will be always equal to 1. That's my original idea, but it's never panned out. I'll show you why. So if we have the so-called fuzzy partition, then for each input point, the summation of all membership functions will be equal to 1. Sorry, I should be more precise. The summation of all rules firing strength will be equal to 1. So you don't need to have the normalization layer. So I also propose a parameter identification by hybrid learning. Here we have the consequent of a premise part here, and the consequent part here. Or here you can also call it antecedent part. For the premise part, we have the parameter for membership function. So it's nonlinear parameter, compared to the output of the whole system. But on the other hand, for the rule output, all the parameters are linear. So it's once you have a nonlinear part and linear part, so we can do hybrid learning. Actually, there are 2 pairs in each epoch. For the forward pairs, the premise parameter is fixed, so we can use least square estimate to identify the best parameter. Just once computation of least square. But for the backward pairs, the consequent parameters are fixed. And then we use backpropagation to update the premise parameter. So by doing this, there are several advantages. It should be clear later on. So another view is you can look at the parameter rise of this system. You can MVIS can be seen as only the premise parameter, because once the premise parameters are fixed, the consequent parameter will be determined directly. In other words, the consequent parameters depends on the premise parameter. So actually, there are many models with nonlinear and linear paths, like some of the exponentials, or a neural network with linear output, or the radial basis function network, or even the decision tree. The output can be a constant, that should be the linear path. So by separating, and the advantage of MVIS is obviously it's a universal approximator, because you can partition the input space into very small region. So let me. So it's a universal approximator, and because the depth of the network is only 4 or 5 layers, there's no problem of gradient vanishing like the traditional deep neural network. And because we are using least square estimate, there are a large body of literature we can use, to do, for instance, cross-validation or, outlier detection, input selection, so on and so forth. So the parameter identification, we can use the so-called Gauss-Newton method. The concept is pretty simple. You linearize the fuzzy model, and then use least square estimate to update the parameter incrementally. And yet another better method is Leverberg-McQuarrie. The formula is like this. The original one is the Gauss-Newton method, but you plus lambda times a identity matrix. Then you can change the lambda. When lambda is small, this one is close to 0, then you have a Gauss-Newton method. But when lambda is big, you are approaching gradient descent. Then we can control the value of lambda. If we want to adopt greedy policy, we can make lambda small. On the other hand, if we want to take cautious policy, then we can make lambda large. Actually, I think Leverberg-McQuarrie is one of the best methods, to identify the parameter for, data fitting. But actually, there are, a spectrum of methods you can do it. If you use gradient descent, then you can simply treat all parameters as nonlinear. If you use hybrid learning, then you use gradient descent plus least square estimator. And by using this hybrid learning method, it can be adapted, for pattern by pattern learning. So especially for online adaptive control. And you can use Gauss-Newton, you linearize all parameters. And you can use Leverberg-McQuarrie, you switch smoothly between gradient descent and the Gauss-Newton method. So there's a huge body of literature of optimization to tune the parameter of emphasis. Now let's take a look at the structure identification. We want to identify the best structure for emphasis modeling. One thing is brutal force, just use grid partitioning. Then it will lead to curse of dimensionality. Then we propose to use CART as a preprocessing to do the structure identification. Of course, we can do scatter partitioning, but I don't think there is a good method for this. So we will stick to CART method for structure identification. So CART stands for classification and regression tree. It should be pretty straightforward. For instance, for this kind of input space, we can first put a cut on x equal to a, and another cut on y equal to b. We can get the region of A1. So if y is greater than a and x is greater than a and y is greater than b, then z is f1. This is the rule for this region. And then the rule for second region right here. The third rule, the fourth rule. It's pretty straightforward. But if the output is a constant, if we plot the surface, you can see it's a piecewise flat. So it's hard to do gradient descent. Usually it's almost impossible. But on the other hand, if the output of each rule is a linear function, then it's piecewise linear surface. It's not continuous. So presumably, because it's not continuous, so the generalization capability will not be so good. So one thing we can do some improvement is to introduce the membership function for x greater than c. You can use a sinusoidal function like this, or you can use an S-shaped membership function like this. And if we plug the membership function into the original equation, then you are going to get a surface like this. It's much more smoother, And by doing some fine tuning, I think it will be able to generate a better result. And this is the result when the output of each rule is a linear equation. So I propose the use use of the CART algorithm as a preprocessing for emphasis. So this is the corresponding fuzzy if-then rules. If you change these rules into MV structure, you'll find that actually you don't need the normalization layer, because all the summation of the membership grade will always be equal to 1. So it will be a lot simpler to use MVs. Here we have a 3 membership function, and this is an inverse or negation of the membership function. Then we multiply to get the weight of each rule, and we multiply the weight with the output of each rule and do a summation, and we got a Z here. There's no need to do normalization because all the weights here will always sum to 1. So here we have a table. For cut, the structure identification we can perform to have an input selection, but there's no fine tuning. For MVs, if you don't do any structure identification, we can use the naive, grid partition. Then it will lead to the curse of dimensionality. But MVs, you can do fine tuning, so you can combine the strengths of both sides to get a better result. Then, because it's based on the MVs is based on least square estimate, so there's a huge body of literature of using the least square estimate to do some other stuff. For instance, we can do leave one out cross validation. Then it will be easier to identify the outlier in the data set. Especially if you are using naive computation of least square estimate for leave one out. The complexity will be O to the n squared. And we can use incremental update for leave one out. The complexity will be much lower. And we did try this method on the paper by Sugeno. The paper was published in 1993. And eventually we identified there's an outlier right here. There are 2 curves here. The curve close to 0.2 is the training root mean square error. And the curve, on the other hand, is up and down, is the test or validation root mean square error. But for these data points, the deviation is so large, so we can safely conclude this is an outlier. And when I check the paper, because the paper has listed all the data set, and there's a specific number is deviated from the others. So I think it must be some kind of error during the manuscript editing. And of course, we can do feature selection. We can use, as you know, there are 3 types of feature selection: filter method, wrapper methods, and embedding method. If we are using filter method, we can use Pearson correlation or ANOVA analysis. And if we are using wrapper method, we can use sequential forward or backward selection, or use exhaustive selection. And of course, the best one is to use embedding method. So we can do feature selection by cut, then do model refinement by cut-based MVs. Here I have listed some paper right here. It's all pretty old. And as you can see, I'm always the single author. There's a story behind it. From 95 to from 90 to the year 2000, almost all my fuzzy related paper are single author. Because for the first 5 years, my advisor, FUZZ-IEEE, he told me you have to do independent research. So I'm single author. For the next 5 years, from 95 to 2000, I couldn't find any PhD students. So I need to do independent research because I don't have any students. So at that time, fuzzy is not so popular. Neural network is not so popular either. So at the year 2001, I decided to change the name of my lab from Neural Fuzzy Lab to Multimedia Information Retrieval Lab. So that's why I left the fuzzy community because I couldn't find any students. So that's also the reason why there are so many single authors of my paper on fuzzy stuff. And of course, you can do some fuzzy extraction, but this concept is not really mature yet. We can change the output of the training data into an interval output. Then you convert the regression problem to classification. Then we can use LDA for feature extraction. But the objective function is not really for regression. So actually we need to do some tweaking of the objective function for linear discriminant analysis. So the citation of FUZZ is pretty high. As of today, the citation is close to 23,000. So I'm going to explain why the citation is high. First, right before I joined the Mathwork, I decided to release all the C code and the data set. Because once I joined the company, it's hard for me to release anything. So I try to clean up the C code and the data set and release it. Actually, I spent about 1 month to write a C code for FUZZ. At that time, I was not very good at the C code. So I check and check, especially for memory leak. I do a lot of checking. And I also use numerical method to check if the gradient is right or not. So I'm pretty sure the FUZZ code should be correct, no problem at all. And for all the example I put into the FUZZ paper, I didn't tweak the parameter too much. I just do it, and the performance is much higher than neural network. The reason is pretty simple, because I use least square estimate. It's a very efficient method for data feeding. So everyone got my code and got my data set. They only need to do a little bit improvement, then can get better result and publish paper. And I also implemented FUZZ in Fuzzy Logic Toolbox. I also co-authored the book Neural Fuzzy and the Soft Computing. It's also encouraged by Professor Zade to convert my PhD dissertation into a book. And I'm the single author, as I say. Professor Zade told me I need to do independent research. Actually, he only corrected my English because he was so busy, so he doesn't know what I'm working on. But that's why I'm the single author. Also, I've done some extension to FUZZ. So if you want to have your paper as high citation, you need to follow this guideline. You need always to release the code. Don't make your example so hard, to surpass. Let other people to do something for you. Then your paper will get high submission, just like me. And of course, you need to be old enough. If you are too young, there's no way to get a high citation. So I've been teaching in the university for 30 years. And then, actually I was always, when I first get back to Taiwan in Tsinghua University, they have the so-called 6-year rule. If you don't advance from assistant professor to associate professor, you're going to be kicked out of the university. So I was so panicked because I don't have any students. No one want to do neural and fuzzy. That's why I decided to change the direction of my lab. But when I was advanced to the full professor at the year 2009, it's pretty easy because at that time we have a Google citation. Google Scholar appeared in the end of 2004. So it's simple for me to show the citation number to the people who can decide that I can advance to the full professor or not. So I should thank to Google for them to help me. Otherwise, there's no way to know your impact of your papers. So let's take a look at how to use Levenberg plot for FUZZ. So this is a single input, single output problem. Here we have the dots. The dots here are the training data, and the curve here is the output of the FUZZ. So this is the initial membership function by using hybrid learning. and this is the final membership function. So the membership function, they don't change too much, but the fitting is not so good. You can see here, the fitting is bad. The fitting is bad here. But if I change to Levenberg-McQuarrie, you can see the accuracy is much better. The root-mean square error is much error. You can see the fitting here is pretty good, although the fitting here is still not so good. But the problem is, the membership function changed a lot. You lose the linguistic meaning of the membership function. So here we have another example. Here we have 4 rules using for the, use the same data set. The hybrid learning do a pretty good job, and the Levenberg-McQuarrie also do an even better job. The root-mean square error is also much lower. As you can see, the membership function, they are overlapping each other. You lose all the semantic information about these linguistic terms. So that's why I want to, here we have example. On the x-axis is the explainability. On the y-axis is the mapping precision of the model. For neural network, no matter how you do the training, it's always at a position at a pretty low explainability. For MVIS, you start from a pretty good initial configuration with good explainability. And if you use this square estimate only, you are going up. You keep the explainability. If you use hybrid learning, the membership function will change a little bit. So the explainability will getting lower a little bit, but the mapping precision is higher. On the other hand, if you use Levenberg-McQuarrie, you have a higher mapping precision, but you lose the explainability. So that's why I'm saying by using the hybrid learning, you use gradient descent for membership function, it will simply fall into the nearest local minimum. It's not bad because you keep more or less the membership function, and then you keep the linguistic meaning of the membership function. So I would like to propose how we can do explainability preserving learning in MFIS. We want to present the explainability. Of course, in this conference, you can see there are many papers, many presentations explaining about the explainability in AI. So different people has different view. And my definition is pretty simple. Does that make sense to a human? And if you look at the input-output, can you feel the rule, of each of the original fuzzy if-then rules? And let me show you. For this one, this is a crisp case. You define 3 regions, and for each region, you define a linear function. So there's no fuzzy at all, but the explainability is pretty clear. But if you fuzzify this, you get a continuous curve, but then continuous and differentiable curve. But the explainability is a little bit lower. Then after learning, you get this kind of curve. Then the explainability is pretty low. As you can see, the dominant membership function for this region is membership function 2. For this part is membership function 1. For this part again is membership function 2. For this part is membership function 3. So the order has been changed. So again, you lose the linguistic interpretation. So how can we try to make MVIS after learning? How can we try to preserve the explainability? One thing is a good choice of membership function. It should be normal. This is pretty straightforward. And it should be convex. This is non-convex. So this part is straightforward. Then we need to have a fuzzy partition. All the summation of the membership function be equal to 1. Or for this kind of crisp condition, if the summation is equal to 1. For the second one, the summation is more or less close to 1, because we didn't try to make them equal to 1. but it's pretty close. But for this kind of membership function, the summation is up and down, so you lose the linguistic meaning. And then the second one is we want to have, for each given input data, we want to have a dominant membership function instead of many membership functions contributing equally to the summation. So we can use the so-called impurity function. We can use the entropy function or the Gini index to find the impurity of the probability vector p equal to p1 till pn. When n is equal to 1, we can plot p1. Because p1 plus p2 is equal to 1, then we can plot p1 only, so the maximum appear to be 0.5 here. And for n is equal to 3, we can plot the entropy service, and the maximum point will be at the 1/3 for both x and y. For Gini index is the same. So we want to make it less fuzzy, then it will be more explainable. So we want to have a dominant membership function. Then let's take a look at here. If you have a crisp example, the entropy is most of the time is pretty low. Then you have a fuzzy case here. The entropy will go up here because there are some equally contributing factor from membership 1 and membership 2 here. And on the other hand, you have this kind of not so regular membership function. The entropy is going up and down. It's always higher than the, for instance, if we define the threshold to be 0.2, then you should be much, this case is much higher than 0.2. Then how do we define a loss function to low entropy? For this case, we have the entropy function like here. And there are two methods. One is to find the alpha cut. If alpha is equal to 0.5, we have alpha cut here. So the ratio between alpha cut and the universe of this code should be low. But computation-wise, this method is a little bit complicated. Another method is pretty simple. You can minimize the area under the entropy curve. So you can define the loss function in order to achieve low entropy. And how about the order? We want to preserve the order. For this case, the order is 1, 2, 3 is pretty good. But after learning, you may switch the order of membership function. A1 becomes here, A2 was moved to here, so the order becomes 2, 1, 3. It's not so good. We need to keep the linguistic meaning. And for this case, of course, we have a 2, 1, 2, 3. 2 is dominant here, 1 is dominant here, and 2 is dominant here, 3 is here. So it's 2, 1, 2, 3. So how can we define a loss function for this kind of order? So we can simply adopt the loss function for learning to rate. And once you have the loss function, we can use gradient descent to optimize the whole system. And for the consequent part, it's pretty straightforward. If we have order equal to 0, it's constant, so it's pretty explainable. Order equal to 1 is a line or a plane, is also explainable. But when order is equal to 2, then it's getting more or less fuzzier. So when we increase the order, we decrease the explainability. So this is summary. If we want to keep the explainability in MFIS after learning, we use normal convex membership function. We hope to have a fuzzy partition of the membership function. We want to the result, the membership function after learning should have a low entropy. And later on, and the last one, we want to have a reasonable order. So all the above criteria can be formulated into a loss function, and we can use gradient descent to optimize the whole system. 10 minutes. 10 minutes, okay. Yeah, I use deep research to find the MFIS application by Keynote. There are a bunch of applications. Then
Oh, this way.
student. Then I use deep research to find the advantage and the disadvantage of MPs. Then I get a conflict view. For instance, here the advantage is interpretability, but the disadvantage is interpretability challenging. This one, the advantage is high accuracy and the generation capability. The disadvantage here is tendency to overfit. And here is computational efficiency. Here, and on the other hand, is high computational cost. So it's like conflicting view. But actually, you can explain all these advantage and the disadvantage in different contexts. For instance, tendency to overfit. That's because the least square estimate is very efficient in doing data fitting. So you need to create the regularization term in order to prevent the model from overfitting. Okay. So why gradient descent is good? I think it's good because it's simple formula. You can do hardware, software implementation. It's universally applicable if each component of the system is continuous. As long as the component is continuous, you can do differentiation. So you can use max, min. For instance, if you are using fuzzy reasoning, you are taking the minima of all the antecedent part. Still, you can use gradient descent. But sometimes, if it's not continuously, we can make it continuous using fuzzy logic. For instance, like this one, it's not continuous. So if you want to perform gradient descent, the loss function is a piecewise flat. Unless you change this boundary across a data point, then you will change the loss function. So one simple way is to just use fuzzy concept, and it's easier to do gradient descent. So I think fuzzy logic or fuzzy set will always be laid, except that sometimes people don't call it fuzzy, but it will always be laid. So here we have some GD example, but since we don't have time, I'm going to skip some of the application of gradient descent on control system and on placement system. So people would like to ask, since I'm in a bank for 5 years, what do we do in the bank? So there's a predictive AI application at the Yisan Bank. There are a lot. For instance, when you use your credit card, all the transaction data will be sent back to the Yisan server, and we are using machine learning to determine is a fraud transaction or not. And also, for instance, house price prediction. When someone apply for a mortgage, we want to do a estimation of the house price. I won't go into details. There are so many of them. And we have also generative AI application at Yisan Bank. Again, there are a lot of applications. So for the bank, my position is to try to apply all the AI technology to the operation in the bank. But most of the time, it's not a problem of technology. It's a problem of talking. I need to talk to the business unit to tell them what kind of operation can be replaced by AI. So I spend most of the time in a meeting and talk to them. And my official title is CTO, Chief Technology Officer. I think it's more appropriate to change it to T's Talk, Chief Talk Officer, because I was talking all the time. So, for instance, this is an interesting example of the using the CRISP rule to do scam account detection. Let me read this. If a person sets up more than n different scheduled transfer recipients within a month, and there is at least one day within the recent M day when the account shows rapid fund inflow and outflow, with the ratio of inflow and outflow goes 1 to 1, then the system will flag this as a abnormal. So actually inside the bank, there are so many rules. This is only 3 of them out of 39. When I try to request a rule, actually they are hesitant to give me. They ask me, what do you want to do? I told them I want to show this rule to an audience in an international conference and explain to them how we can use fuzzy logic to enhance this rule. And he said, no, I can only give you 3 and I'll change the number. Because once these rules are released or leaked to the scam syndicate or scam ring, they will try to find ways to bypass this rule. So this is very sensitive information. So how do we embedding membership function into CRISP rule? It's pretty easy. Whenever there's a number, you change it into a membership function. For instance, more than n different schedule transfer recipient, we can use a sigmoidal function here, and n is equal to 5 here. And within a month, we can use another different direction of sigmoidal function. Then 30 days is right here. Once you fuzzify all the number in the rule, then you can define inverse mechanism and loss function. Then you can optimize the overall system by gradient descent. So this is a pretty straightforward method for using fuzzy logic. So the advantage of using the same rule structure, you can make the system almost completely explainable. Here is the explanation of the rule. This pattern reflects phase paster, repetitive form, so on and so forth. So whenever they create the rules, they put explanation right here. And all we need to do is change it into a fuzzy version. Then another advantage is you can gain the trust of domain experts who design the CRISP rules. It's really hard to convince them to use machine learning model. But by using an intermediate step of introducing this kind of fuzzy state, you can make the system explainable and trustworthy. I think I'll skip this one. Okay. The simple observation is talk is cheap. We should focus more on application and code in order to define the future direction of fuzzy state or fuzzy logic. So here is the final slide. I hope it's not too late. And Envis is only a thing. We need more people to work on open source software and the real world data set. I think this is the right direction for this fuzzy community. But I truly enjoy coming back to this community. It's small, but it's beautiful. Everyone knows everyone. So it's a very nice community. And the real-world human-centered AI system require explainability and trustworthiness, especially in the bank and in the hospital. I have been working in the hospital for 2 years and the bank for 5 years. As Chinese saying goes, 一个是要钱，一个是要命的地方. In the bank, they want your money. In the hospital, they want your life. So it's a very conservative institution. So you need to have explainability and trustworthy. Otherwise, they won't take the AI system. And then the final, my observation is gradient descent is simple but yet effective for optimization. And once you introduce the fuzzy set into a CRISP rules, then fuzzy set becomes a very good companion for gradient descent to optimize the whole system. Okay, that concludes my talk. Thank you for your attention. If you have any question, welcome to ask. Thank you.
Thank you very much for this very nice talk, Professor Jang. We have room for a few questions. Yes, I think I saw.
Thank you for the interesting talk. Okay, so from your talk, correct me if my understanding is wrong. Here. Okay. So if we add more membership functions, so then does it mean that the explainability will be tends to reduce? So in certain cases, if we add more membership functions, then it will add for us the rooms to have a better models. So does it mean the explainability will reduce?
It all depends on your choice. If you have a membership function, suppose you have enough data set, that's good, because you don't need to adapt the membership function too much. So you keep the original explainable structure. On the other hand, if you have many membership functions and the data is so complicated, then the membership function will be changed a lot. Then you lose the linguistic meaning. So it all depends.
Thank you very much for your interesting presentation. I'm a big fan of FUZZ and I use it a lot in my research for the argument of explainability. But I also keep wondering, you show explainability and precision or accuracy, and you show that if you push FUZZ, you can get the precision you're looking for. Why do you think multi-layer perceptron is beating FUZZ and used more computer vision transformer architecture when FUZZ can also be used as a universal approximator?
You say why the neural network doesn't have a good explainability?
No. Why neural network is preferred over FUZZ if both can approximate a function, but FUZZ is better in terms of explainability?
Okay.
Is it possible to turn on the slides? You need to tell them into the microphone.
Is it possible to turn on the slides officially, sleep?
I tried to.
I could start right here, but not here.
Oh,
Yeah.
Can you turn on the slides, please?
okay, good.
Okay, this is based on my intuition. Because for neural network, it's hard to have any kind of interpretation, especially for deep learning neural network. So even if the mapping precision is good, you still get a pretty low explainability. But for NVIS, because the initial structure is a rule structure, so the explainability is good initially, right here. But then during the training, if you use D2S method, it's going up. You keep the same explainability. If you use hybrid learning network, you change the membership function a little bit, but the explainability is still good. On the other hand, if you use development quad, the mapping precision is pretty high, but you lose the explainability because the membership function has been changed a lot. Maybe one on top of the other, or you have the spike-like membership function. So that's my intuition. Yeah. There's no rigorous proof. This is based on my empirical experiment.
Yes, thank you for your presentation. I think with your presentation, I think you addressed maybe the main issue we discussed in the panel just before your presentation, how to, let's say, popularize or promote a new breakthrough in fuzzy logic to big companies like MathWorks, and you did it, so that's great. But if you don't mind, can you maybe share some more details about the whole process? For example, did you have to be proactive to go to MathWorks and ask them to implement ANFIS, or did they chase you because you had a lot of citations? Of course, you don't have to. It's great to know something more about the whole process.
So, sorry, do you mean, do I need to instruct my students to do the implementation?
No, I was just talking about the implementation of ANFIS in the fuzzy logic toolbox by MathWorks. Because I think it was implemented just a few years, correct me if I'm wrong, after your first publication, which was a great illustration of how science could be promoted to companies.
Yeah.
So that's my question, if you could share some more details about the process.
At that time, when I joined the MathWorks, and I have another co-author, so we two together finished the fuzzy logic toolbox. The other guy is a native speaker, so he's good at writing manual. So I'm doing all the coding. And in fact, there are a lot of animation. I didn't show you here. It's all constructed by me. So at that time, actually, as you can see, Actually, I don't like to write papers. I like to do coding and to create something useful. That's why I joined the math work. Otherwise, I could have joined Bell Lab, or IBM, so on and so forth. So I think the fuzzy logic toolbox is pretty nice. So if you have any question, you feel free to send me questions. Thank you.
Okay, I think in view of time we should stop, but Professor Jang is here the remainder of the day, so at the banquet or in between, I'm sure if you have further questions you will have a chance to discuss. So let's thank him one more time. And also thank you for attending this plenary session. In 15 minutes we will continue, so you'll have